Welcome back to Physics 191. I'm Gerard Blanchard. And before we go on today, I would like to summarize what we talked about last time. We talked about Newton's first law: an object at rest remains at rest, or an object in motion remains in motion at constant speed in a straight line unless acted on by an unbalanced force, which we summarize simply to in equilibrium. Equilibrium being either static equilibrium, an object at rest remains at rest, or dynamic equilibrium, an object in motion remains in motion at constant speed in a straight line. In equilibrium, the total force on an object is equal to zero. The total force vector on an object is equal to zero. So we took that Newton's first law, defined a situation in which you can apply Newton's first law. We called it an equilibrium situation. And whenever you have an equilibrium situation, you can always write down as your starting equation, total force vector is equal to zero, which also is two component equations. Every vector equation is two component equations, which would be the total force in the x direction is equal to zero, the total force in the y direction is equal to zero. You can always start from there in an equilibrium situation. So once you recognize an equilibrium situation, you go through our process, you draw a diagram, you list your knowns and unknowns, you write down your starting equation, and then you work from there. That is the process that we'll be working with all semester long. There's going to be more situations. Later today, we'll define a non-equilibrium situation and what to do with that. But before we get on to that, I would like to introduce you to Newton's third law. We're going to skip the second law and come back to that in the next chapter. Newton's third law, as you can see written here on the slide, translated, Newton's third law says, the forces of two bodies on each other are always equal and are directed in opposite directions. You will often hear that translated as, or paraphrased as, for every action there's an equal and opposite reaction. Well, that's a little bit confusing because the term action and reaction has changed meanings over the years. When that law was expressed as for every action there's an equal and opposite reaction, the word action and reaction meant force. Action meant what we now call force. So a better way to say Newton's third law is for every force there is an equal and opposite force. And so what that means is simply that. For every force there is an equal and opposite force. For example, if you have an object sitting on a desk, then the object pushes down on the desk and the desk pushes up on the object with an equal and opposite force. Whenever one object pulls on another object, whenever object 1 pulls on object 2 pulls back on object 1 with an equal and opposite force. Sometimes you have to train yourself to visualize these forces, and once again that goes back to the skills that you need in physics. You have to visualize things that might not be immediately opposite. So finally, we can express Newton's third law with an equation. That's our procedure here. We put everything in an equation so that we can apply it mathematically to our models. Our equation would be that the force vector by object A on object B equals minus force vector by object B on object A. And remember that every vector equation is two component equations, so that means that if object A is pushing in the x direction on object B, then object B is pushing in the negative x direction on object A with an equal and opposite force. Let us take an example so that you can begin to visualize these forces. In this example, you have a horse pulling a sleigh over snow, and the question is asking you to draw 3 force diagrams. One for the horse, one for the sleigh, and one for the horse and sleigh taken as a unit. So what I would like you to do is to draw the horse. Doesn't have to be a great picture. I'm actually going to use boxes. I will have a square horse. The sleigh, draw the sleigh, and then draw all of the forces on the horse, draw all of the forces on the sleigh, and then in a third diagram, the horse and the sleigh together will be a single object or a single box. So please try that. Please draw all of the forces on the horse, all of the forces on the sleigh, and all the forces on the horse and sleigh together. And I would like you to think about it. Once again, remember, try to do this so that you can see what you're thinking, and then you can learn, you can see that your thinking was correct, or you can learn where you can make some improvement. So please try. Okay, let me draw my horse. As I said, I'm just going to draw a square horse. And my sleigh, I'll draw a square sleigh. In these diagrams, the important thing are the forces, not the quality of your drawing. Let's start to draw in the forces on the horse and the sleigh. Well, we know that gravity is pulling down on the horse. So we have the weight of the horse pulling it down, and we have the weight of the sleigh. We also know that the ground is pushing up on the horse and the sleigh, so we have to draw in the normal force on the horse and the normal force on the sleigh. Okay, well, those are all of our forces in the vertical direction, weight down, normal force up. Let's think about the other forces that must exist. Well, we can imagine that there's friction on the sleigh, and the friction as a sleigh slides across the ground is opposing its motion. So that would be kinetic friction on the sleigh. Well, the diagram said that the horse and the sleigh were moving forward at constant speed, so there must be a balancing force to the kinetic friction on the sleigh. Well, that must be the force that the horse applies on the sleigh, and I'll write FHS, the force of the horse on the sleigh. Well, if the horse is exerting a force on the sleigh, then by Newton's third law, we know that the sleigh must be exerting a force on the horse. And so that would be the force of the sleigh on the horse. And we know that that must be equal in magnitude, and opposite in direction. So we know that the force of the sleigh on the horse is pointing back towards the sleigh. And we know furthermore that these two forces are equal in magnitude. So we know that the force of the horse on the sleigh is equal in magnitude to the force of the sleigh on the horse. They have the same amount of force, but they're opposite, meaning they're opposite in direction, as I've drawn these two arrows in opposite directions. Well, we're not done with the horse yet, and we know that we're not done because if the horse is in dynamic equilibrium, there must be a force pushing forward on the horse. What could that force be? Well, how does the horse move? The horse moves by pushing on the ground. The horse exerts a force on the ground, but that's not a force on the horse. That's a force on the ground. But by Newton's third law, we know that if the horse exerts a force on the ground, then the ground must exert a force on the horse. So we know that there is a force that the ground is exerting on the horse. And that force is, in fact, equal and opposite to the force that the horse exerts on the ground. So the horse, and this is important, the horse does not push himself forward. The horse pushes backwards on the ground. The ground, therefore, pushes forward on the horse, and it is the forward force of the ground on the horse that keeps the horse moving at constant speed. That is, once again, something that you have to learn to visualize. This may not be immediately obvious at first glance, but if you think about Newton's third law, you begin to realize that it has to be there. The horse cannot push on himself. You can't pick yourself up by your own bootstraps, but the horse can push on the ground, and it's the pushing on the ground that causes the ground to push on the horse, and it's the ground pushing on the horse that moves him forward. If you want to think about this a little bit more, think about if the horse were on an infinitely slippery ice surface, an ice surface with no friction at all. Well, the horse can try to push all he wants, but if the horse cannot push on the ice, then the ice cannot push the horse forward, and the horse will not move forward. So it is the force of the ground pushing on the horse that's keeping him going forward. Okay. Those are the forces on those objects. So if you got those, great. If not, think about where your diagram differed from this diagram. Finally, let's do the horse and the sleigh as a unit. And this is something that you will see in future exercises, is that sometimes you can choose whether to separate objects into separate objects or to treat them as one large object. We'll talk about more about that later. Well, if we consider the horse plus the sleigh as an object, well, we have all the same forces. We have the force of the ground on the horse. We have the normal force on the horse. We have the normal force on the sleigh. We have kinetic friction pulling on the sleigh, now pulling on the sleigh plus horse. We have the weight of the sleigh, and we have the weight of the horse. And now we have to add in, or we have to consider adding in the force of the horse on the sleigh and the force of the sleigh on the horse. But as you can see, those are equal in magnitude, opposite in direction, so they cancel out. When we consider the sleigh and the horse as a unit, then the forces between the horse and the sleigh become what we would call internal forces. And we, in Physics 191, when we're dealing with the motion of objects as a whole, we don't have to worry about internal forces. So we do not have to write the force of the sleigh pulling on the horse or the force of the horse pulling on the sleigh, because those cancel out. All of these internal forces cancel out. So if we were treating the horse and the sleigh as a single unit, we would have normal force, and we could add those together. Weight, and we can add those together. It'd just be the weight of the sleigh and plus the weight of the horse. The force that the ground exerts on the horse, and the kinetic friction exerted on the sleigh. And those would be the forces exerted on the sleigh and the horse as a unit. Now, when you break up an object into separate objects or treat it as a single object, that's a matter of experience. And we're going to be working exercises to get you experience so that you can see which would be more appropriate in your mathematical models. that is the end of Chapter 2 for us. And we're going to move on to Chapter 3. Chapter 3, titled Acceleration in Newton's Second Law of Motion, is just that. We're going to talk about Newton's second law and acceleration. Newton's second law. Once again, I'll spare you the Latin. Newton's second law, translated from the Latin in which Newton wrote, is the alteration of motion is proportional to the unbalanced force impressed and is in the direction in which that unbalanced force is impressed. There's another part that is implicit in Newton's second law. It's actually found in when Newton wrote the Principia Mathematica, it's actually found in the third law, and that is that the change of the velocity is inversely proportional to the mass. We're going to take both of those into our equation for Newton's second law. If we paraphrase these two statements into modern English, we would say that the acceleration of an object is proportional to the total force vector acting on that object and inversely proportional to the mass of the object. Or, as we do, we'll put that in an equation form. And finally, we would say that in the absence of equilibrium, when we do not have equilibrium, when we do not have the conditions for a static or dynamic equilibrium, then we have another equation, and that equation is acceleration vector is equal to total force vector divided by mass. Acceleration vector is equal to total force vector divided by mass. Note that acceleration is a vector, force is a vector. The direction of acceleration and the direction of force are important, but mass is a scalar. It doesn't have direction. The amount of mass you have does not have a direction, so your two vector quantities in that equation are acceleration and force. So when we break this vector equation into two separate component equations, you will have acceleration in the x direction is equal to total force in the x direction divided by mass. Mass does not have x or y components. Mass is just mass. So that brings us to our second type of situation that you'll encounter in Physics 191. And we'll call this a non-equilibrium situation. How do you identify a non-equilibrium situation? Simply that the situation is not equilibrium. It's not static equilibrium, and it's not dynamic equilibrium. So non-equilibrium means we don't have equilibrium. Our starting equation is acceleration vector is equal to total force vector divided by mass. So this is the equation we're going to be using throughout most of this chapter. This is the equation that you will apply to your mathematical models for whatever situation comes up. Acceleration vector equals total force vector divided by mass. In components, that would be the acceleration in the x direction is equal to the total force in the x direction divided by mass. No x component on mass. And acceleration in the y direction is equal to the total force in the y direction divided by mass. So mass is mass. Whether it's in the x equation or the y equation, it's the same mass. And that might be important for solving some questions that you're asked later on. Now, one important thing to realize is that a situation can be a mixture of equilibrium and non-equilibrium, meaning that you could have equilibrium in the y direction but not in the x direction, or vice versa. So you can have a mix of equilibrium and non-equilibrium. Let's go right into an example, and this is a non-equilibrium situation. The problem statement is a 2010 kilogram elevator moves with a downward acceleration. Notice where you're given a direction of the acceleration, which is necessary because acceleration is a vector. The downward acceleration of 1.5 meters per second squared. What is the tension in the cable that supports the elevator? So I would like you to spend some time trying to answer this question. What you should do, you should draw a diagram. You should list all of your knowns and unknowns. You should recognize that this is a non-equilibrium situation. Since it's accelerating, that means it's not moving at constant speed. And that would mean that we would use Newton's second law. So this equation will use acceleration vector is equal to total force vector divided by mass. So try, and I will, in a moment, I will begin to walk you through this exercise. Okay, let's create our model of this situation. We start with an elevator. Once again, a box, E for elevator. We know that the mass of the elevator, we were given the mass of the elevator is equal to 2,010 kilograms. That's one of our knowns. We are told that the acceleration is equal to 1.5 meters per second squared downward. So we had to draw an arrow downward indicating that the acceleration is downward. We are told that there is a cable supporting the elevator, so I'll draw that in. And we know that the tension is supporting the elevator, and we know that the tension force will be in the direction of the cable, so I will draw that up. We have to think about what other forces would be acting on the elevator, and there's only one, and that is the weight of the elevator. So we have weight, and we know that weight is equal in magnitude to mass times g. And I'll go over here and I'll calculate that. Weight is equal to mass times g. Weight is equal to a mass of 2,010 kilograms. Now I'm going to keep my units in here for this first exercise because there's an important point to make about the units of acceleration. Times g, which is 9.8 newtons per kilogram. And so we have a weight of 19,700 newtons. 19,700 newtons. And how do I know it's newtons? Well, here I have kilograms divided by kilograms, and I'm left with units of newtons. So we know that the weight is equal to 19,700 newtons. And so we've drawn in all of our knowns. We've drawn in everything that we know at this point about the situation. What is our unknown? Well, it's tension. Tension is our unknown. We're looking for tension. Now we have to write our starting equation. We think, is this elevator in equilibrium? Is it moving at constant speed in a straight line? And the answer is no. It's accelerating, which means that its speed is changing. Well, since we know that we have non-equilibrium, we can use our equation. Acceleration is equal to force divided by mass. Actually, those are vectors. Acceleration vector is equal to total force vector divided by mass. Well, let me put in my coordinate axes, y and x. And in this case, we're really only interested in the y-axis, since the elevator is accelerating downwards and all of the forces are in the y direction. So this would become acceleration in the y direction is equal to, and this should be force total, is equal to force total in the y direction divided by mass. Slide this up just a little bit. And so we can start filling in with what we know. The acceleration in the y direction is 1.5 meters per second squared. But it's not in the positive y direction. That would be upwards. It's in the negative y direction, so I have to write negative. Negative 1.5 meters per second squared is equal to the total of all of the forces in the y direction divided by the mass of the elevator. Well, let's think about that. We have to find our forces in the positive y direction. Well, there's only one force in the positive y direction, and that's the tension. So we have tension in the positive y direction. Do we have forces in the negative y direction? Yes, that's the weight. So since weight is in the negative y direction, it'd be tension minus 19,700 newtons. And then, so that is our total force. Our total force is the tension minus 19,700 newtons. And now we have to divide by the mass, and the mass is 2,010 kilograms. We have our equation. We only have one unknown in there, tension, so all we have to do at this point is to solve this equation for tension. We'll start off by multiplying both sides by 2,010 kilograms. So that would be minus 1.5 meters per second squared times 2,010 kilograms is equal to tension minus 19,700 newtons. Well, we can calculate this out right here. That gives us 3,015, or negative 3,015. It's a comma, 3,015. And what are our units? Well, we have a kilogram times a meter per second squared. If you remember from our definition of a newton, that is a newton. A kilogram times a meter per second squared is a newton. So instead of writing kilogram meter per second squared, I'll write newton. And that's good because now you can see that all of our terms have units of newtons. So minus 3,015 newtons is equal to tension minus 19,700 newtons. Well, next I'll have to add 19,700 newtons to both sides, and I have 19,700 newtons. I've added that to both sides, minus 3,015 newtons is equal to tension. Well, 19,700 newtons minus 3,015 newtons gives us, I'm going to round off to 16,700 newtons equals tension. Push that up. And we've answered the question that we were asked, which was, what is the tension in the cable? The tension in the cable is 16,700 newtons. You'll notice that that's less than the weight. The weight was 19,700 newtons. Well, if you have 16,700 newtons of tension in the cable pulling up, 19,700 newtons of weight pulling down on the elevator, it's not in equilibrium, which means it will accelerate. So that's our example of Newton's second law. When you have unbalanced forces, the object will accelerate, or conversely, if the object is accelerating, then we know that the forces are not balanced. And those are both contained in this, both of those ideas are contained in this one equation. The acceleration vector is equal to the total force vector divided by the mass. And the other important thing to see here is that you will have to convert sometimes between a newton and a kilogram meter per second squared, or sometimes you'll have a newton divided by a kilogram, which will give you a meter per second squared. But as long as we're working in basic metric units, the newton is the basic metric unit of force, meter per second squared is the basic metric unit of acceleration. Why that is, we'll get to a little bit later. As long as you're in basic metric units, everything will work out. Okay, let's do another example. In this example, it talks about an accelerometer that consists simply of a pendulum, an object suspended from a string. And the problem statement says, an accelerometer, a device to measure acceleration, can be as simple as a small pendulum. Suppose you're flying a small plane in a straight horizontal line, and your accelerometer hangs 12 degrees behind the vertical, as shown in the picture. What is your acceleration at that time? And you've probably encountered this in a car as well. If you're in a car and you have something hanging from your rear view mirror and you accelerate forwards, the object will swing backwards against the acceleration. So in this example, we'll see why that is. So what I would like you to do is to draw your diagram and think of all the forces acting on the pendulum and see if you can make a head start on figuring out the acceleration of the airplane in this case. Okay, let's draw a diagram. I'm going to let me draw a box for the airplane. And the airplane, we're told, is accelerating. So that is the direction of the acceleration of the airplane and all the contents in the airplane. It says that the airplane is flying in a straight horizontal line. That means that the airplane is not moving upwards or downwards. So in the vertical direction, and I'll go ahead and let me draw some axes so we can discuss this in terms of axes. I'll make this my x-axis and this my y-axis. In the y-axis, the airplane is in equilibrium. The airplane is not accelerating in the y direction. If we just considered its y position is not changing and it stays not changing. So we know that the airplane and all of its contents are in equilibrium in the y direction. So I'm going to go ahead and write that down already. We'll need that. Y equilibrium. And in x, the airplane is accelerating horizontally, it's accelerating in the x direction, so we have x non-equilibrium. So we already know what our starting equations are going to be. And I'll go ahead and write them down. for non-equilibrium, we write down Newton's second law, or the acceleration in the x direction is equal to the total force in the x direction divided by the mass, total force in the x direction, there we go. And in the y direction, we have equilibrium, so we know that the total force in the y direction is equal to 0. So for the airplane, for all the contents of the airplane, these two equations will hold. Well, we need a particular object to apply them to. That would be the pendulum bob, the object suspended from the string. So let me go ahead and draw in the string, the ball. The ball has a certain mass. We don't know what the mass is. As it turns out, we'll be able to solve this exercise without knowing what the mass is. We do know that the string makes an angle of 12 degrees with the vertical. Okay, let's think about the forces on that mass. The forces on the mass are the weight. Weight is equal to mass times g. We know that much. And so weight would be equal to mass, which we don't know, times 9.8 newtons per kilogram. We don't know what the weight is, but we know that the weight is whatever the mass is, times 9.8 newtons per kilogram. What other forces are acting on the ball? Well, there's only one other, and that is the tension in the string. And we know that tension acts in the direction of the string. So I will draw my tension vector along the string. And we need to start thinking about x and y components. Well, the weight is completely in the y direction. Tension is in both the x direction and the y direction, so we will have to break tension up into x and y components, or in other words, if the tension is up and to the right, then we can break that up into an up component and a y component. And so the up component would be ty, and that's also the side that's adjacent to the angle. So I'll also write ty is equal to t adjacent. And similarly for x. Tension in the x direction would be tension opposite. So whenever you have force vectors that are not aligned with your x and y axes, you'll have to break them up into components, which means to make a right triangle, one side being in the x direction, one side being in the y direction. Okay, any other forces acting on the ball that's hanging from the string? We're just thinking about the ball now. Any other forces? And the answer is no. There are no more forces acting on that ball. So now we'll have to go to our equations and see where that leads us. I should say we have now drawn in all of the knowns and all of the unknowns. The acceleration is an unknown. Tension at the moment is an unknown. And so is mass. Mass is an unknown. So we've drawn in all of our knowns and unknowns. We've identified non-equilibrium in the x direction, equilibrium in the y direction. And so it might not be obvious how we're going to get our answer, but we know that the answer is in those equations somewhere. We have to trust that. Somewhere in there, the answer is somewhere in those equations. Well, let's see what we can do with that. Acceleration in the x direction. That's what we're looking for. So I'm just going to leave that as ax. Total force in the x direction. Well, there's only one force in the x direction, and that is tx. And we know that tx is equal to t opposite. So I'm going to write t opposite divided by mass. Well, there's one thing we can do with t opposite. We know that t opposite, acceleration in the x direction, is equal to t opposite. T opposite is the side that's opposite to the angle, and we know that the opposite side is equal to the hypotenuse times sine of 12 degrees. So it's equal, the acceleration in the x direction is equal to the tension times the sine of 12 degrees. That's t opposite divided by our mass. We have one equation with three unknowns in there. Well, there's nothing further we can do right now. We'll have to try our y equation. Let's go over to our y equation and see what happens. In our y equation, we have the total force in the y direction is equal to 0. What do we have in the positive y direction? We have ty, and ty is equal to t adjacent. So I'll go ahead and write that. T adjacent. In the negative y direction, we have the weight. I'll just go ahead and write weight to begin with. And we know that t adjacent minus weight is equal to 0. Well, if t adjacent minus weight is equal to 0, we know that t adjacent is equal to weight. We find that just by writing out, by adding weight to both sides. Well, what is t adjacent? What do we know about t adjacent? We know that the adjacent side is equal to the hypotenuse, t, times the cosine of the angle, which is 12 degrees. Tension cosine 12 degrees is equal to the weight. And we know that weight is equal to the mass times 9.8. And I'm not going to write my units. We're in basic metric units, and I know that, so I can have confidence that my answers will also be in basic metric units. So we know that tension cosine of 12 degrees is equal to whatever the mass is, times 9.8. Well, let's solve that for tension. Solve that for tension. We'll divide both sides by cosine of 12. And we have tension is equal to mass times 9.8 divided by cosine of 12 degrees. Let's take that now and substitute it back into our x equation. I'm going to take tension, substitute it back into here, and we have the acceleration in the x direction is equal to mass times 9.8 divided by cosine of 12 degrees. That much is just t. That is t. We know that t is equal to mass times 9.8 divided by cosine of 12 degrees. So we can write that in the place of t. But now we need to multiply by sine of 12 degrees and divide by mass. And notice what happens here. Notice how we get away with not knowing the mass. We have mass divided by mass. So that will always be equal to 1 regardless of what the mass is. That means that our answer doesn't depend on the mass of the object that we hang from the ceiling or from our rearview mirror if it's a car. And notice that on this side now, we know everything. We know what 9.8 is. We can calculate the sine of 12. We can calculate the cosine of 12. Actually, if you recognize from your trigonometry, sine of 12 divided by cosine of 12 is tangent of 12. So you could actually save yourself one step of calculation. Just use tangent of 12. Well, what is the acceleration? AX is equal to, and I'm going to go ahead and calculate it as 9.8 times tangent of 12 equals 2.08. 2.08. And I know that I'll have to have basic metric units for my acceleration, so that would be 2.08 meters per second squared. So regardless of what the mass is, the acceleration is 2.08 meters per second squared. This situation will come up frequently, that you'll wind up having mass in the numerator and mass in the denominator, and you won't have to know the mass. The answer to your situation won't depend on mass. So if you think you need to know the mass, but the situation doesn't tell you the mass, well, try anyway. Especially when you have weight. Notice that weight depends on mass. Acceleration has mass in the denominator when you have force divided by mass. So often that mass will simply cancel out and be unimportant. Okay, that's another example of using Newton's second law in a non-equilibrium situation. How do we recognize non-equilibrium situations? Well, the word acceleration is a giveaway. Acceleration means that you're not moving at constant speed. Remember that for equilibrium, you have to be at rest and remaining at rest, or moving at constant speed in a straight line, and if you're accelerating, that's violated. So acceleration, the word acceleration is a hint that you're dealing with a non-equilibrium situation, but realize that you could have acceleration in one direction and equilibrium in the other direction. And in fact, you can always orient your coordinate axes so that acceleration is pointed along one direction. So actually you can always have a mixture between equilibrium and non-equilibrium. When you have equilibrium, the appropriate equation is total force in that direction equals 0. When you have non-equilibrium, the appropriate starting equation is the total force in that direction divided by the mass equals the acceleration in that direction. And even if you don't know how the answer is going to come out of that, trust me, the answer is in there. So follow this procedure and the answer is in there somewhere. Next time we're going to do more examples of non-equilibrium situations. This is a very important category of situations that you're going to face. So we'll pick up with that next time. Until then, think physics.